Hello students, welcome to the class of complex analysis. So in this video we are following the textbook J.B. Conway Functions of One Complex Variable second edition. Okay. So as you know, a complex number set can be considered as x plus iy, where x is equal to real part of z and y equal to imaginary part of z. And every complex number x plus iy can be identified as the pair of real numbers xy, so that the complex number c and the plane R2 are isomorphic to each other. Okay, now in this video we are going to check out what are the properties of and examples of analytic functions. So we are dealing with what are the analytic functions. Analytic functions. So what a complex function w equal to fz is said to be analytic at a point z naught. We recall the definition of analyticity. Okay, suppose f is said to be analytic at a point z naught, analytic at a point z naught in some domain if f is differentiable at z naught and there exists at least one neighborhood of z naught for which the f should be differentiable throughout that domain, and there exists some neighborhood of z naught at which f is differentiable throughout the neighborhood. So such kind of function is said to be analytic at the point z naught. Okay, when a function is analytic throughout the domain, we say that is an analytic function in that domain. And a function which is analytic everywhere in the complex plane is called an entire function. Entire means analytic everywhere in the complex plane. Analytic everywhere in the complex plane. Okay. Now we are going to find out what are the properties of analytic function in terms of power series. Okay. Now, what is the definition of a convergence of complex series? So suppose we have a series sigma an, which is a series of complex numbers, and we say that sigma an converges to a complex number set if for every epsilon greater than 0 there exists a natural number n such that the difference between nth sum sigma n equal to 0 to some m an minus that complex number is less than epsilon for every m greater than or equal to n. Actually, which means that a series of complex number is said to be convergent to a complex number set if its nth partial sum, the sequence of nth partial sum is convergent to the same number set. Okay, which is the definition of convergence of complex series. Convergence of series of complex numbers. Sigma an said to be convergent to a complex number set if for every epsilon greater than 0 there exists a natural number. There is a stage such that the mth sequence of partial sum converges to the same set. Okay, and as we know, every absolutely convergent series is convergent. What is meant by the absolute convergence? If a series sigma an is said to be absolutely convergent, absolutely convergent if sigma mod an is convergent. When a series is absolutely convergent, it means that its modulus sigma mod an is convergent. Okay, and we can prove that every absolutely convergent series is convergent. Every absolutely convergent series is always convergent. So how will you prove this proposition? Suppose assume sigma an is a convergent series, absolutely convergent series. Okay, so when it is an absolutely convergent series, which means that sigma mod an is convergent. sigma mod an is convergent. So as per the definition of convergence, I choose let epsilon be greater than 0. Then I take the partial sum Zn is equal to sequence of partial sum Zn equal to a0 plus a1 plus a2 plus etc plus some an. Then since sigma mod an is convergent, there exists an integer n such that we can write sigma the sequence of partial sum or the tail of the series is convergent. That means I can write some n equal to k plus 1 to infinity mod an is less than epsilon, which means that the tail of the series is very small, negligible amount. Okay, and it is possible only when we have a convergent series, right? Now in order to prove sigma an convergent, we have to prove that its sequence of partial sum is convergent, and its sequence of partial sum is Zn. Nth term of the sequence of partial sum of sigma an is denoted by Zn. That means to prove sigma an convergent, we prove the sequence of partial sum of sigma an, which is equal to Zn, is a convergent sequence. So for that consider modulus of Zm minus Zk. So by definition this can be written modulus of sigma. What is Zn? Zn equal to sum of first n numbers from the series sigma an. Then Zm will be sum of first n numbers. So that will be n equal to some 0 to m Zn or an. Okay. Minus this is sigma n equal to 0 to some k an. So that is equal to when you assume m is greater than or equal to k greater than or equal to that fixed integer n, consider m and k such that then this can be considered as sigma 0 to m minus 0 to k will be k plus 1 to m. Sigma n equal to k plus 1 to m an. Okay, and modulus of summation is always less or equal to summation of modulus n equal to k plus 1 to m. And what is this? This is actually the always less than or equal to, which is actually always less than or equal to sigma n equal to k plus 1 to infinity mod an. And what is this? This is the tail of series of sigma mod an, and we know that sigma mod an is convergent, therefore its tail of series is negligible, which can be less than epsilon. Since sigma mod an is convergent, its tail of series is very small, so which is can be less than epsilon, and this is true for every n and m greater than or equal to that fixed integer n. Okay, so which means that the series Zm, the sequence Zn is a convergent sequence. Is a convergent, or in particular this is a Cauchy sequence. Zm minus Zk is less than epsilon for every n and m greater than or equal to n means after the stage any two members of the sequence is very small, which means that the sequence Zn is a Cauchy sequence in the complex plane C. And we know that the complex plane is a complete space, so every sequence is converges in it. Since the complex plane C is complete, every Cauchy sequence converges in it. Therefore, Zn should be converges in it, which implies there exists some complex number Z in the complex plane such that the sequence Zn converges to that set. So, which means that limit n tends to infinity, the sequence Zn equal to small z. So whenever the sequence of partial sum Zn converges to a complex number, which means that the corresponding series sigma an is converges to the same number set. which implies sigma an converges. So every absolutely summable sequence is summable, or every absolutely convergent series is summable. Now we recall what was the definition of limit superior and limit inferior in real numbers. So for that, let an be a sequence, in real number. Okay, then we define limit inferior of the sequence an, which is equal to limit n tends to infinity, infimum of the sequence an plus 1, an plus 2, etc. This is actually which means in a similar way we can define limit inferior, that is limit supremum of an, and that is equal to limit n tends to infinity supremum of the sequence an plus 1, etc. Now how will you find out these limits? So that is which actually means that when we take I take b1 equal to supremum of the sequence a1, a2, etc. the given sequence. Then you take b2 is equal to supremum of a2, a3, etc. We are shifting the sequence actually. We are actually eliminating the first term of the sequence for b2. And what will be b3? b3 will be supremum of a3, a4, a5, etc. So if you define b1, b2, etc. like this, then you find out infimum of bn over n. Infimum of bn will be equal to infimum of supremum k greater than, or this can be written supremum k greater than or equal to n. Okay, infimum over n ak. Okay, this can be written like this. And what is this? This is actually called the limit superior of the sequence an. So in a simple way we can find out like this. Now to prove the limit inferior, this is called a limit superior, and for defining limit inferior we will consider the same some b1 dash, b2 dash, etc. Now consider b1 dash equal to the same. In a similar way, instead of supremum we take the infimum of a1, a2, etc. and b2 dash is equal to infimum of a2, a3, etc., etc. Then you find out the supremum of bn dash, which is equal to supremum over n infimum of n less than or equal to k ak, and which is called the limit inferior of the sequence an. Okay, this is called the definition of limit inferior, and which is called the limit superior, and it is called the limit inferior. So ഈ രീതിയിൽ നമുക്ക് ഒരു സീക്വൻസിന്റെ ലിമിറ്റ് ഇൻഫീരിയറും ലിമിറ്റ് സുപ്പീരിയറും ഡിഫൈൻ ചെയ്യാൻ പറ്റും. This is in the case of real numbers. So ഇതേപോലെ നമുക്ക് in a similar way we can define limit inferior and limit superior of complex sequences also. Okay, now we will define what is the complex power series about a point A. Okay, a power series about a point A is an infinite series of the form sigma n equal to 0 to infinity some an into z minus a raised to n, which is the format of a complex power series about the point A, where an's are called coefficients and A is the center point. Okay, so one of the simplest example is the geometric series. So complex geometric series is of the form sigma n equal to 0 to infinity z raised to n, where the center point is 0, z minus a, where a is taken as 0, so a equal to 0. Okay, so it is of the form sigma n equal to 0 to infinity z raised to n. Okay, now Now we will see what about the convergence of this series. Okay, now consider 1 minus z raised to n plus 1. What is this? This can be considered as 1 raised to n plus 1 minus z raised to n plus 1. So a raised to n minus b raised to n formula ഉപയോഗിച്ച് കഴിഞ്ഞാൽ this can be written 1 minus z into, okay, a minus b into 1 plus a z plus z square plus z cube plus etc. plus z raised to n. So this can be considered as 1 minus z into 1 plus z square plus etc. plus z raised to n. Okay, and that is equal to 1 minus z raised to n plus 1 divided by 1 minus z can be written 1 plus z square plus etc. plus z raised to n. And that is 1 minus z raised to n plus 1 by 1 minus z can be written sigma z raised to n equal to 0 to infinity. So our geometric series sigma n equal to 0 to infinity z raised to n can be written 1 minus z raised to n plus 1 divided by 1 minus z. Okay, now what will happen if mod z is less than 1? If mod z is less than 1, then limit n tends to infinity. Mod z less than 1 എന്ന് പറഞ്ഞാൽ actually what is the meaning of mod z less than 1? We are considering the elements inside or interior of the unit circle with the radius with the center 0. So ഇതാണ് നമ്മുടെ കോംപ്ലെക്സ് പ്ലെയിൻ എങ്കിൽ mod z ലെസ് ദാൻ 1 എന്ന് പറഞ്ഞാൽ this is the circle mod z equal to 1. Then we are considering the elements from interior of this circle. So all of them have value or which they are always closer to the center point is 0. So limit n tends to infinity, modulus of z raised to n will actually equal to 0. Which are near to 0, therefore it converges to 0 as n tends to infinity. So which implies limit n tends to infinity z raised to n is actually equal to 0. Okay, when the nth term goes to 0, the series is convergent, right? Therefore, as n tends to infinity, our series is convergent. Sigma n equal to 0 to infinity z raised to n is actually convergent. And where it goes to 1 minus 0 divided by 1 minus z, and that is equal to 1 by 1 minus z. When mod z is less than 1, our geometric series, complex geometric series converges to 1 by 1 minus z. Okay, then what will happen if mod z is greater than 1? Elements are belongs to the exterior of the unit circle. Okay, then when mod z greater than 1, limit n tends to infinity, mod z raised to n will goes to infinity. Okay, therefore the series is divergent. The series is, when nth term goes to infinity, the series is diverges. The series is diverges. Therefore, our geometric series sigma z raised to n equal to 0 to infinity have two cases. One is converges to 1 by 1 minus z if mod z less than 1. If mod z is greater than 1, it is diverges. So this is the result about the geometric series sigma n equal to 0 to infinity z raised to n. Okay, when we have a convergent power series or when we have a power series, we can find out what about its radius convergence. Radius of convergence means under which domain or inside which domain our series is convergent. Okay, so to find out that, we will use the definition of limit supremum or limit superior of the sequences. Okay, so I will define a theorem for a given power series sigma n equal to 0 to infinity a n z minus a raised to n, define the number capital R, 0 less than or equal to r less than or equal to infinity by 1 by r equal to reciprocal of r equal to limit superior of mod a n raised to 1 by n. So the radius of convergence of a power series is defined to be 1 by r equal to limit superior of mod a n raised to 1 by n. Then we have three cases. First one, A, if mod z minus a is less than capital R, then we say that the series is converges absolutely. The series converges absolutely. And second part, if mod z minus a is greater than r, then we say that the terms of the series become unbounded and so the series is diverges. The terms of the series become unbounded and so the series is diverges. Diverges. For the C part, if 0 less than small r less than capital R, then the series converges uniformly on mod z less than or equal to R. Set of all sets such that mod z less than or equal to R. Okay. അതായത് നമുക്കൊരു പവർ സീരീസ് ഉണ്ട് സിഗ്മ n equal to 0 to infinity a n z minus a raised to n എങ്കിൽ we can find out or we can define the radius of convergence of the power series. And radius of convergence എന്ന് പറയുന്നത് ഈ ആറിനെയാണ് വിളിക്കുന്നത്. And how will you find out this r? The number r is called radius of convergence if it is defined by 1 by r equal to limit supremum or limit supremum of mod a n raised to 1 by n. Okay. Then when you find out this r, we can say that when mod z minus a less than r, when our set belongs to the interior of the circle with the center a and radius r, the series become converges absolutely. When it belongs to the exterior of that circle, we say that the series is diverges. When you have a small radius r which is less than capital R, then inside that small radius r, unit circle with or mod z minus actually okay, then the series is converges uniformly. Uniform convergence means it is converges uniformly means that convergence is uniform. That means there is no sudden fluctuations in the series. ഒരു ലാർജ് എമൗണ്ടിലേക്ക് പെട്ടെന്ന് കൺവേർജ് ചെയ്യില്ല, ഒരു സ്മോൾ എമൗണ്ടിലേക്ക് സഡൻലി ഡിക്രീസ് ചെയ്യുക അത് ചെയ്യില്ല. അതാണ് അതിൻ്റെ മീനിങ്. ഓക്കെ, അപ്പോൾ ഇത്രയും റീസൺസ് ഉള്ള അല്ലെങ്കിൽ ഇത്രയും കേസസ് കൺസിഡർ ചെയ്യുന്ന ആർ എന്ന് പറയുന്ന റിയൽ നമ്പറിനെ വിളിക്കുന്ന പേരാണ് where r is called the radius of convergence of the power series. ഓക്കെ, സോ നമ്മളിത് പ്രൂവ് ചെയ്യാൻ പോവാണ്. പ്രൂഫിനകത്ത് നമ്മൾ സെൻറ്റർ പോയിൻ്റ് എ 0 ആയിട്ട് എടുത്തിട്ടാണ് പ്രൂവ് ചെയ്യുന്നത്. സോ ഫോർ ദ പ്രൂഫ് വി വിൽ അസ്യൂം the center point a equal to 0. Okay, so we need only consider the series. Sigma a n z raised to n equal to 0 to infinity. The center term is equal to actually 0. Ready? So to prove this r has these properties, first of all we need to consider this case, mod z minus a less than r. That is, when a equal to 0, we consider mod z less than r. So let mod z is less than r. Okay, then we need to prove that our series is converges absolutely. Okay, since mod z is less than r, what is r? R is the radius of convergence and it is a real number. And what is mod z? When z is a complex number, mod z is always a real number, right? So mod z and capital R are real numbers. So in between two real numbers, we can find out a rational number by density theorem. Okay, so choose a real number r such that mod z less than r less than capital R. In between two real number, we consider another rational real number r. So which means that when r is less than capital R, its reciprocal 1 by r will be less than 1 by small r. Okay, then what is 1 by r? By definition, 1 by r equal to limit supremum of mod a n raised to 1 by r. So this can be written limit supremum of mod a n raised to 1 by n is less than 1 by r. So which means that when limit supremum is 1 by r, what is the definition of limit supremum? This can be written infimum of supremum k greater than or equal to n mod ak raised to 1 by k is less than 1 by r. When infimum of set of elements is less than 1 by r, all the elements will become or there exists, we can consider a positive integer n such that some element will be less than 1 by r. Okay, which implies there is a positive integer capital N such that supremum k greater than or equal to that integer capital N mod ak raised to 1 by k is less than 1 by r. When supremum after the stage of capital N is less than 1 by r, we consider, which implies modulus of an raised to 1 by n is less than 1 by r for every n greater than or equal to that fixed integer. And which means that mod an is less than 1 by r raised to n for every n greater than or equal to that fixed integer. Okay, so mod an is less than 1 by r raised to n. Okay, then what will happen to modulus of an z raised to n? And that can be less than or equal to mod an mod z raised to n. Okay, and what about this mod an? Mod an is strictly less than 1 by r raised to n mod z raised to n. So which can be written mod z by r whole raised to n. Okay, then we assumed that mod z is less than r less than capital R. So which means that mod z by r is strictly less than 1. So when mod z by r is strictly less than 1, mod z by r raised to n sigma is a convergent series, or it is a geometric series. It's a geometric series and it is converges because its common ratio is mod z by r and which is less than 1, right? It is converges. So when which means that when we have two series sigma mod an raised to n equal to 0 to infinity is less than or equal to sigma n equal to 0 to infinity mod z by r raised to n, and this series is converges. Therefore by comparison test this series must converge, right? So which implies sigma n equal to 0 to infinity mod an z raised to n is converges. So mod an converges means it is converges absolutely, right? So sigma n equal to infinity an z raised to n is converges absolutely when mod z is less than r. So when mod z is less than r, we proved that the given series is converges absolutely because its modulus is actually converges. Okay, now to prove the second part, we need to assume mod z minus a is greater than r, and we chosen that a equal to 0. Therefore we consider mod z is greater than r. So mod z greater than r എന്ന് പറയുന്ന കേസിൽ we need to prove that our series is become unbounded and it is diverges. Okay, so for that we consider mod z is greater than r. So take mod z is greater than r. Okay, now again mod z is a real number, r is a real number, so in between real number we choose a rational number. Choose a real number or rational number r such that mod z greater than r greater than capital R. Okay, so which implies when r is greater than capital R, 1 by small r will be greater than 1 by capital R will be greater than 1 by small r. Okay, and 1 by capital R is nothing but by definition limit supremum of mod an raised to 1 by n is greater than 1 by r. So by definition it will be infimum supremum of k greater than or equal to n mod ak raised to 1 by k is greater than 1 by r. Okay, so infimum is greater than means we can choose a number. There is a stage, right, which implies there exists some n such that supremum k greater than or equal to that fixed integer n mod ak raised to 1 by k is greater than 1 by r, which means mod an raised to 1 by n is greater than 1 by r for every n greater than or equal to n. So which means that mod an is greater than 1 by r raised to n. Okay, mod an is greater than 1 by r raised to n. When mod an is greater than 1 by r raised to n, for the corresponding same an, we will consider modulus of an z raised to n. So now consider the for same an, consider mod an z raised to n, and mod an z raised to n can be greater than or equal to mod an mod z raised to which is actually equal to, mod an is, mod an z raised to n will be equal to mod an mod z raised to n, okay. And what is mod an? This is actually greater than 1 by r raised to n mod z raised to n, okay. And this is actually greater than mod z by r whole raised to n. So which means that mod an z raised to n is greater than z by r raised to n. Now we assumed that mod z is greater than r, which is greater than capital R, okay. Therefore mod z by r is greater than 1. When mod z by r is greater than 1, the series sigma which means that sigma an z raised to n is greater than or equal to sigma mod z by r raised to n. Ready? And since z by r is greater than 1, this series become diverges because it is a geometric series with a common ratio greater than 1. Therefore this series is diverges. When this series is diverges, again by comparison test this series become diverges. So which means that the series sigma n equal to 0 to infinity mod an z raised to n is diverges. So which means that sigma n equal to 0 to infinity an z raised to n is also diverges for mod z greater than capital R. Now for the C part, we have to prove that when we have 0 less than r less than capital R, the series is uniformly converges on mod z less than or equal to R. Okay, we need to prove that the series uniformly converges in mod z less than or equal to small r. Okay. So suppose that actually we have to prove that sigma an z raised to n is uniformly converges on mod z less than or equal to small r. So we have to assume this condition first. So I take mod z is less than or equal to r if, okay, and we have this r is small r is less than capital R. So which means that mod z less than or equal to small r and which is less than capital R. Okay. Now since small r and capital R are real numbers, in between these two real number I choose another real number rho. Okay. Now consider a real number rho such that r less than rho less than capital R. Okay. Then what about its reciprocal? 1 by capital R is strictly less than, 1 by rho is strictly less than 1 by small r. Okay. And by definition 1 by r is equal to limit supremum. Limit supremum mod an raised to 1 by n is less than 1 by rho. Okay. So which when limit supremum is less than 1 by rho, there exists a positive integer capital N such that mod an raised to 1 by n is less than 1 by rho for every n greater than or equal to that fixed integer. So which means that mod an is less than 1 by rho raised to n for every n greater than or equal to capital N. അല്ലേ, 1 by n ആണെങ്കിൽ എന്നോട് പവർ n ചെയ്ത് കഴിഞ്ഞാൽ ഇതിൻ്റെ nth പവർ ക്യാൻസൽ ചെയ്ത് പോകും. റെഡി. Then consider for the same an, consider mod an z raised to n, and this will be equal to mod an mod z raised to n, and which will be less than mod z raised to n into 1 by rho raised to n. So this is z by rho whole raised to n less than or equal to. Okay. So and we have mod z is less than small r, right? So which is less than r by rho raised to n, right? And what is r by rho? When r is strictly less than rho, from here we get r by rho is strictly less than 1. When r by rho is less than 1, r by rho raised to n, the corresponding geometric series will become converges. When, okay, now, so which means that sigma mod an z raised to n is less than or equal to sigma r by rho raised to n. Okay. Since r less than rho, r by rho is less than 1. When this is less than 1, this will become a geometric series with common ratio common ratio less than 1. Common ratio less than 1. When common ratio is less than 1, this geometry series become converge, therefore it is converges. Okay, when this the bigger series is convergent, by comparison test this series also convergent, therefore by comparison test sigma mod an z raised to n is convergent. Okay, or by Weierstrass M test it is also convergent. Okay, now here we use actually instead of comparison test we use the Weierstrass M test. So what is Weierstrass M test? Weierstrass M test says that when we have a sequence of positive real numbers mn, when mn is a sequence of positive real numbers such that modulus of fnx is less than or equal to mn for every x in some domain, and if the series sigma mn converges, then sigma fn is uniformly convergent. This was the Weierstrass M test. Okay, so by this test what will happen here sigma r by rho raised to n is convergent, modulus of fnx less than or equal to this mn, this is here mn, r by rho act as some mn. Okay, so by this Weierstrass M test, sigma an z raised to n is uniformly convergent for the same domain for mod z less than or equal to small r. Okay, and this capital R is actually called a radius of convergence. When we have a power series sigma a in mod z minus a raised to n, then if you can find out r such that 1 by r equal to limit supremum of mod a n raised to 1 by n, then when mod z minus a less than r, series become converges absolutely. When mod z minus a greater than r, the series become diverges, and when mod z less r equal to some small r less than capital R, then series will become uniformly convergent, and that radius capital R is called a radius of convergence of the given power series. Okay.